realize after submitting this abstract that this is a pretty difficult room to tell something they don't know about ice. So I'm going to tell you some things I've been surprised to find out about ice shells and environmental considerations. So this is work I've done in support of two different projects. One is a JPL-led study called CROW, which is looking at full mission architectures for accessing ice shell interiors, and we're hoping to share the first results of that at EPSC, DPS, and AGU this fall. So something to look forward to. Quick plug, there's going to be a session I'm co-convening, not dissimilar to this one, at the AGU fall meeting. So if you think you have updates and you can already project them and put them in an abstract and submit it, might be a nice chance to meet. And the other work that I've been supporting is Honeybee's slush proposal in Sesame. So I've listed a few co-authors here, but really I've worked with probably 45 people between these efforts, a lot of which are in the room. So there's all of the usual suspects. This is something I stole out of a slush abstract or a poster. And it's tiny, but you all know what these are. There's diurnally activated cracks and deep faults and the potential for geologic stresses and lakes and salt lenses and acids and all the fun stuff. And so I've set about trying to take a lot of these different abstract ideas to simplify them as much as possible and really look at how you can start to place system-level capability constraints on them. But, oh yeah, I noticed this when I uploaded my talk. It's going to take forever for any animation to happen. So I'll start by mentioning what's about to show up is Aaron Leonard's geologic map, I hope. Thinking about the biggest tectonic worries when you go somewhere. I'm only going to talk about Europa in this talk because it's 11 minutes and there's way too much to talk about in icy satellites. But one result of Aaron's work mapping Europa and thinking about the geologic history has been that the geologic evolution has changed over time. She found that in Europa's earliest period, so that's the first period down here at the bottom, on the x-axis, so today is this third period. On the x-axis, you have all the different kinds of units. And what she found is that if you look at the blue, the very first thing to form on Europa were global regional plains, so large-scale deformation everywhere. And that transitioned to bands, which are still large but more local features, has transitioned to chaos, which are relatively local, and also cracks and craters. So the geology has really changed from widely distributed high stress requirement tectonics to more locally distributed cracks that can form at lower stresses. And so I just had a paper out in Icarus where I look at sort of the stresses and forces available on Europa to deform it today. And my primary anxieties for drilling through an ice shell lie in diurnally active cracks, and I'm not as worried about deep interior faults. So the most impressive thing I do are these movies of ice shells, and so of course I'm going to show them in every talk I give. This is showing an ice shell thawing out from 50 kilometers to a present day ice shell thickness for an estimate of interior silicate heat generation and internal tidal heating. And on the left, the red stuff is stiff and the blue stuff is convecting. And in the middle, I'm tracking the historical freezing rate, which relates to salt composition. And on the right is the age that the ice froze in. Just one quick thing I want to mention here is that when you actually simulate convection on top of an ocean with fully temperature-dependent parameters, it can look much different than the convection models you're used to. Especially because the stagnant lids above convection cells can be much higher proportion of the ice shell. That means that you're going to be in colder, stiffer ice for longer with the potential for fracture porosity and spend less time in the convecting regime near the melting temperature. And so if you plot, I took Barr and Schoeman out of the Europa book, and you often see this parameterization of a convective ice shell thermal structure, the black line. If you plot what convective ice shell thermal structures might look like, they're much closer to something like a conductive shell. There are regimes where I can freeze out ice shells to steady state modern values. And one thing to mention here is that all of this purple stuff are areas where there is entrained partial melt that doesn't immediately drain out. And so you can find regimes where you have a slushy ice-ocean interface. If you're thinking about getting all the way into the water, you might have difficulty detecting a sharp boundary at the ice-ocean interface, and when you get there, it might not be mechanically intact. Another issue with conductive shells, so this is really difficult to see, but on the y-axis is depth through a 15-kilometer shell, And on the x-axis is porosity. So I built a shell with 20% initial porosity, and then I let it bake for 1,000 years up to 65 million years, which is the current surface age of Europa. And one thing you notice that even if you pick a really high starting porosity, you tend to maintain high porosities in about the upper half of a conductive ice shell. So the issue here is, I don't know what porosity Europa's ice shelf froze at, but it sure is fractured, and if fracture porosity is relatively high, and has been throughout its history, it can be retained over geologic time. So porosities more than about 5% are going to keep you connected to the vacuum, and those might not just be a surface problem. These high porosities could extend to depth and persist over geologic time. So you might have kilometers of connection to the vacuum. If I make a relationship between salt content in an ice shell and its freezing rate, you can see all these weird structures start to form when you begin to make ice shells. It's because you start to get small wavelength compositional convection from salts in addition to the thermal convection in the ice. And what this can actually do is it can produce lateral and horizontal heterogeneities in salt content that could build salt hazards into different parts of the ice shell that would be difficult to detect through remote sensing, which could average over these length scales. And so one interesting thing to think about is if you assume the ocean is an Earth salinity, the ice shell on average has to be that salinity or less. And so it's possible that you're going to encounter somewhere or up to 25 kilograms of salt per every meter that you drill. And so if you have a 50 centimeter wide probe, that's a couple centimeters of salt for every meter. And so if you start to pick the geologic object of interest to you, if it's 100 meters tall, a lake or something that you want to freeze out, then you could be talking several meters of salt lenses that you would have to cut through. And the reason I make that comparison is I get asked a lot, what happens if you hit a meteorite or something? And I wanted to compare the amount of endogenic non-ice material to potential exogenic non-ice material. So one way to back of the envelope that is you can take this Alvarello study from 2008, where they simulate a bunch of, I'm going to start with stuff from Io. So they simulate impacts on Io and how Io ejecta might end up on Europa. They look at the distribution of Io material on the surface and find that there's a dependence on both latitude and longitude of that material distribution. And so something I've done is you can build probability maps of where Io material is going to land. So this is yellow is more likely to have material deposited on it and blue is not. So there can be latitudinal and longitudinal dependencies in the amount of non-ice material you might have to drill through. And you can look at total fluxes from Io to Europa and start to think about how much over 65 million years you could accumulate. So, for example, if you have a 50 centimeter diameter drill because you want to stick a nuclear reactor or something in it, you only have to deal with about 10 kilograms of non-ice material every kilometer you drill. If you're going with a finless RTG or stripping out your GPHS bricks from your RTG, you can get thinner and you have to deal with less material. Even if you include primary impacts on Europa from other bodies, these numbers are still extremely small, about 1,000th of what you have to worry about with salt, potentially. And so one fun thing is you can think about what happens if every projectile that hits Europa is broken up into the worst size pieces, so pieces on the scale of your drill. That's not how the universe works, but even if it were in that worst case, you only have about a 1% chance for a 10 centimeter borehole of hitting an object that is the same size as your drill or bigger. And you only have about a 0.6% chance if it's 50 centimeters. And of course, in a reality, you tend to create many, many more small objects on an impact than you retain large objects, and so this is going to skew further to the left. And I think the chances of really having to worry about more than just the occasional dust in the ice from exogenic material is pretty low. So for me, the primary things that are driving system capability definition is I really worry about tidal shear stresses, especially on tethers. I think Kate and her team are doing great work looking at how diurnal flexing of real tethers might cause them to break. If the ice shell was formed with significant fracture porosity, it could have retained that porosity, and that means you can remain connected to the vacuum for significant depths. So you might not just have to build pressure caps near the surface, you might have to build them the whole way. And it may be that only a small proportion of the ice shell is convecting, especially if you're aiming for a 15-kilometer ice shell, there's probably very little ductile portion. There's very poor constraints on composition in general, including how and where salt is distributed. And so trying to think about the physical processes that drive that, which is something a lot of people in this room do, is extremely useful for planning purposes. In that really the dangers from exogenic non-ice material are pretty trivial compared to the amount of soluble non-ice material you're going to have to deal with as you go through an ice shell. And among the many other things I don't have time to talk about, there's the potential for sublimating salt lags on the surface that you're going to have to break through. Clath rates, if they're stable in your Europa's ice shell, could be a large problem. They're a large problem in terrestrial drilling. And also small-scale variations in your melt jacket volume. If you have small changes in the amount, or in the volume of your melt jacket, or the amount of heat you're putting into, or out of your drill, you can result in perturbations in the volume of that cavity. And if you're in the elastic part of the ice, you can have significant instantaneous pressure changes that could fracture ice. It could force your melt jacket outwards into the ice. Or if you under pressure, you can destabilize that melt cavity. And so these are the things I'm worried about. You're free to worry about other things, but I just wanted to share. Thanks.